Well, what you have up on the screen is a survey of galaxies. Each one of those points is a galaxy. This is a data set taken by the Sloan Digital Sky Survey. It observed over 8 years from a telescope at Apache Point and built up this data set. The survey should have about 1 million galaxies. I've only plotted about 300,000 of them. And what you see is something incredibly rich. You see big agglomerations, you see voids, you see walls, you see something that we call the cosmic web. Now, why are we interested in the cosmic web? Over the last 100 years, cosmology has given us a way of looking at this data set, something like this, and extracting fundamental properties of the universe, how fast it's expanding, how heavy it is, what it's made up of. By looking at the way that this data set is structured, we think we can say something about the very beginning of time, about the Big Bang. So basically, we want to take this data set and we want to access this knowledge about the universe which is in it. Now, that's the challenge. It's very difficult to get this knowledge out of this data set. Buried in this complexity, buried in all this structure, buried in this imperfection is that information. It's not just sitting there. We can't just harvest it. We can't just take it out. And this is what we're facing in cosmology at the moment, and I think many fields of science and knowledge are facing. So I'm just going to give you 2 examples of how we have to tackle something like this, a problem like this. You have a data set and you want to extract information. You basically, one of the things you want to do is you want to compare it to a model. And what we're trying to do here is model the universe. I'm going to limit that a bit. We're trying to model the visible universe, something which is about 1 billion light years across, which is peppered with about 1 billion galaxies. And each galaxy has about 100 million stars, 100 billion stars. So you can see it already that it's just something immense. This universe it follows the laws of physics that we understand. On the one hand, we want to get everything right on the very largest scales. We want to model the universe. On the other hand, we want to be able to extract bits of this model that look like what we see around us. We're buried in the Milky Way, which is something on much smaller scales. So you have to come up with methods of simulating these very disparate scales. And this is an attempt at doing this by some of my colleagues in the project. This is the Mare Nostrum simulation. In this simulation, and what you're seeing here is these wisps of light are basically galaxies, distributions of galaxies, those same galaxies that you saw in the data set. This simulation was run on I'm going to show you a picture of it, a beautiful supercomputer, which is basically housed in a chapel in Barcelona. It's the very postmodern supercomputer. But this simulation took about 4 months to run on tens of thousands of processors. This simulation pushed this computer to the limits. It's designed, basically you want to run something which simulates something on this scale. It pushed the limits of this machine. And it's been used, for example, to recalibrate, to redesign this machine. It really is one of the biggest simulations of this type ever done. Now, these are the kind of scales we're facing. We need to run codes like this on very big machines, but we also need to access this information. And one of the things that you realize with a simulation like this is you run it on such a supercomputer, and you can't just download the data onto your desktop. You need supercomputers to analyze the data which was run on these supercomputers. And so that's one of the challenges that we're facing. How, even though we have these models, how do we make them not just black boxes? How can we extract the real information from the simulations? So this is one example of the type of challenges we're facing. Another challenge is that survey, they had all those white dots. Now, each one of those dots is a galaxy, and each galaxy is a personality in its own right. Here's a selection of galaxies on the screen. Some of them are spiral, some of them are ellipticals, some of them are neither. They're called irregulars. And what they look like, their shapes, hold a lot of information about the evolution of the universe and the actual state of the universe. And we would like to access that information in these galaxies. Now, it turns out that computers aren't very good at getting these images and telling you what they are. They get a lot of it wrong. They will say that a spiral is an irregular. They might say that an elliptical is a spiral. There aren't very good methods of actually classifying these galaxies using computers. Humans are much better. You have, in the Sloan Digital Sky Survey, you have about 1 million galaxies, so you're not going to get half a dozen researchers going through 1 million images classifying them. So one of my colleagues who's sitting in the audience here had the brilliant idea of setting something up called Galaxy Zoo. Now with Galaxy Zoo, it's a site, a website, where any member of the public can access it, can log in, and they'll be shown pictures of galaxies. And for each of these pictures, they're asked a few simple questions. The original question was, is it spiral, is it elliptical? Here are slightly more subtle questions. And basically, they look at each picture, they classify them, and then they see another picture, and they can do many pictures along the way. Now, it's interesting because people are really enthused by this. Just to give you an idea of how well this has worked, this has been around for about 3 years, and in 3 years, we've had something like 150 million classifications by 300,000 people. So it's an incredible success. The public really want to take part in the doing of science. And it's not just the simple doing of science, of just doing these rote procedures. They're fascinated by seeing these images of the cosmos that very few people have actually seen. But more than that, they look at images like this and they look for stuff in them. So very interesting, one of the very interesting things that's come out of this project is people look at these images and they found these green dots, which, you know, no one was looking for. And they started talking to each other on the forums connected to this website. And they realized that they were in lots of images. And they convinced the astronomers to go out and look at these things properly. The astronomers went out and looked at these things properly and found that indeed these green things were sites of star formation, incredibly important places where stars were being born. So that came out of the public's access to the data, and it drove the science in these data sets. So here is an example of where you have these masses of data sets, and you harness the public to help you do your work. Now, things are going to get worse or better. It depends on how you look at it. These are two telescopes which are in the making. One is the Large Synoptic Survey Telescope, which is going to be based in the Atacama Desert in Chile. And the one below is the Square Kilometre Array. It's a radio telescope which will be possibly built in South Africa, possibly in Australia, possibly in both. And this takes the game to a completely new level. Basically, these instruments will videotape the whole visible universe. What will come out of these instruments is time shots of 1 billion galaxies. Not 1 million, 1 billion galaxies. So the data challenge is even more immense than what we've been facing. Now, it's pretty clear, it should be pretty clear that the problems that we're facing in cosmology are very similar, that the problems are being faced in a number of scientific fields, in biodiversity, in economics, in climate science, in oceanography. And we believe that the methods that we're developing can be applied in these other fields. Let me just give you an example. The zoo universe, which is kind of the umbrella for the Galaxy Zoo. In the next few weeks, we'll be launching a project where they'll be taking ship's logs from the First World War, and they'll be asking members of the public to extract information from these ship's logs, things like the temperature of the ocean, the temperature, the wind speed, things like that. In doing so, members of the public will basically amass a very clear and precise and accurate map of the weather around the world during a period of time in the past. At the same time that they're accessing these fascinating bits of information, these ship's logs where lots of things are going on. And there are a number of examples that we're working on where we're basically using the methods that we're developing and we're looking outside our field and seeing how they can be applied.
Thanks very much, Pedro.